Video talks about the MATLAB code that I'd like you to use to explore pulse shapes and symbol synchronization and bandwidth and soft decision diagrams and probability of error, all those kind of things. Okay, so first of all, we have a message signal that we can use, but I've later come up with a different message signal. Okay, so this different message signal has 10,000 data points, which makes it a little better for simulations. So you can add comment or take these out and use different types of message signals, a real one or a random one. All right, so we're doing random. All right, then for this code, we have an upsample factor of 10, which means for every symbol interval, I am sending 10 samples. All right, so my overall sampling rate is going to be, or sampling period is 1 times 10 to the minus 6th. So, 1 over the sample period gives you the sampling rate. So we have 1 megasample per second. All right, this is just a parameter that we choose for speed of transmission. We can change that and everything scales accordingly. All right, so we're familiar with what happens next. We've generated YPAM, our symbols. We know about upsampling. Then in this step, we know about generating the Y-up sequence that gives you something to convolve with a pulse shape to give you the waveform that you're going to use for transmission. Okay, so the first step, you're supposed to uncomment. All right, so normally these would be commented out, and so we put this back in. We're going to look at a triangle waveform, and this is pulse 1. So we're going to answer questions about pulse 1. So I'm going to run this code, and when I run it, it should produce a let's see how that word all fits in. This should produce code that makes this subplot that has, in this first window here, this has the pulse shape. So we see we have a triangle pulse shape. This starts at sample 1 and ends at sample 9. Okay, so that's one of the quiz questions. So come over here to the quiz. The first thing you're supposed to find is the M-sync value that will produce a distortion-free soft decision diagram. Okay, so here's the waveform, and here's an eye diagram, and this gives you the spectrum using the my bandwidth routine that I sent you a different assignment about. And so I look at the soft decision diagram, and I notice I get nice clean lines, but the amplitude is not right? This is 0.6, 0.2, minus 0.2, minus 0.6. So we're sampling at 1, and that's way over here in the pulse, and we want to sample where the pulse is, equal to 1. All right, so I look at this eye diagram, and I see, it looks like the eye is wide open at 5 and 15. We're expecting multiples of M because we have M samples in every symbol. All right, so it looks like M sync should be 5. Okay, so that's the answer to the first question. The second question, this pulse, it has a duration of 9. All right, we're going to later change that, have longer duration pulses, and we'll check out the bandwidth on that. Okay. Question 3, it says turn off the noise by setting sig to 0. All right, so before we do that, let's fix the M-sync parameter. We make that 5. We run our code, and we get what we expected, where the soft decision diagram is now producing the correct symbol values. All right. So next, what I want to do is add some noise into here. All right. Before I do that, let me look at the bandwidth of the signal. Okay. So we pull this back up. The next question is, what is the bandwidth of this signal? And with the my bandwidth command, you can see the part that's in the 90, I think I used 99% energy here, right? Because I used 0.99, that's 99% of the energy shows up in this red band. Okay, so the bandwidth is 136.2 kilohertz. All right, so you choose the closest value, and there's some randomness to this. So another time that I ran it was 136.4. So choose the closest one. That would be 136.4. Okay. So what I also wanted you to notice, as part of the quiz question, I wanted you to notice that if I add noise, I'm going to rerun this with the sigma value of the noise power is 0.2. Okay. And what I get, the second waveform on in the subplot here shows a few symbols, and you can see we have triangle pulses. No noise added to that, but you can see some noise riding along these pulses. This becomes really apparent in the eye diagram. Notice the eyes are still open, so we would expect a probability of error to be 0. So you can find that. I put that in the title of the soft decision diagram. The soft decision diagram, that code, if you look inside the box, it will actually do a little bit of correlation and try to sync the soft decision symbols to the original message signal and determine if you can do the proper frame synchronization to give you a good probability of error. So at 0.2, we're not generating any errors, okay? But notice what happened to the bandwidth. The bandwidth went way up because you're adding a bunch of noise power in there, and that kind of messes up the calculation. And so it's important when we're looking at the bandwidth of the noise-free signal, we set sigma back to 0. Rerun this, and we get the bandwidth estimate. Okay, so everything's looking good on this one. The symbols are correct. We have 0 errors. And we have the bandwidth. So next, what I want you to do is start bumping up the noise power in increments of 0.1. So if I do 0.1, I see there's starting to be some variation in the soft decision diagram, but everything's still well separated. I don't get any of the reds crossing into the blues or yellows crossing up the blues or any kind of mixing of these colors. All right, so I can look here. The probability of error given in the title is 0. All right, so let's bump the power up. All right, the question on the quiz says to try to find which power, or which sigma value, technically it wouldn't be a power, it would be square root of power. Which sigma value gives me something for a probability of error that's close to 0.01. So put 0.2 in there, rerun that, and we look and we see, they're getting closer. Maybe, nope, you look at probability of error, still nothing crosses over at 0.2. No way. All right, so let's bump it up to 0.3. Okay, so at 0.3, I'm starting to generate some errors, but it's very rare, 0.0003. So just a few symbol values cross over at that noise level. Okay, so we keep going up. Go to 0.4. Add more noise in. The eyes starting to look like they're closed, but on average, you only have a 1% probability of error. Actually, that's a significant probability of error for a communication system. Things would start, being unreliable to a certain degree at that point. Okay. All right, so that's the value that we were wanting. Sigma equal 0.4 would be the choice on the quiz. All right, so if I scroll up here, see, you didn't put the rest of the answers in yet, but if you had a range of choices, you'd choose 0.4. Okay. All right, and then the next question I had was, given that you have a noise level set to 0.4, okay, right. Set it to 0.4. Change the symbol synchronization parameter between 5 and 4. Well, we already had it on 5. That's correctly synced. So we're going to intentionally make it not as well synced. All right, so it's going to sync up at 4 instead of 5, and we're wondering, what does that do to the probability of error? So I hit run, and I look at the graph, and I see that this error comes up to almost tenfold, 0.09. Okay, 9-fold times increase in probability of error by just having a one sample synchronization error. One sample instead of one symbol. Okay, so when you look at the answer to that, it looks like the probability of error is significantly increased because of the symbol timing error. All right, that might not be the case for all pulse shapes, so you get the idea. What I want you to do is explore all these things as you run examples of this code. All right, so this is the answer for pulse 1. So you can go through there and do that quiz by using this video. And then I'm going to generate similar quizzes for other pulse shapes.
Uh-oh.